early 1944, at Wright Field near Dayton, Ohio. A test pilot rested his hand on the P-51 Mustang's throttle and nudged it beyond the usual war emergency setting. The engine thundered as boost climbed to 75 inches of mercury while the airplane drank an experimental fuel labeled simply 150 grade. The airspeed needle passed marks that pushed past previously recorded top speeds for Allied fighters. At 25,000 feet, the Mustang was accelerating through 448 mph. Engineers, watching from the ground, exchanged looks as the radio carried the pilot's transmission. This was not a small improvement. It was a transformational leap enabled by purple-dyed aviation gasoline, a chemical edge so large it would invalidate many of the Luftwaffe's assumptions about American fighters. The balance of air combat over Europe was poised to shift, not because of a novel airframe or a clever tactic, but because a new fuel let existing fighters reach performance levels the Germans had not anticipated. What the Reich did not yet appreciate was that Allied fuel scientists had produced something the Third Reich's synthetic fuel industry could not match. While most German fighters were limited to B4 fuel with about 91 octane on the lean scale, and their best C3 blend only approached the Allies' lower high-performance fuels, American refineries were turning out aviation gasoline with a performance number around 150. The consequences were enormous. A P-51 on standard 130-grade fuel could manage roughly 437 nm at 25,000 feet. That same airplane, flown the same way at the same altitude on 150-grade fuel, could top 448 MPH. German aviators, who already respected the Mustang's range and high-altitude ability, were about to find the playing field fundamentally altered. In early 1944, the Messerschmitt Bf 109G, the Luftwaffe's primary single-seat fighter, had a top speed near 400 mph at altitude. The Focke-Wulf 190A could reach about 408 mph under ideal conditions. Against Mustangs operating on 130-grade fuel, German pilots could still seek engagements where they had the advantage. Against Mustangs on 150-grade fuel, those same German fighters faced an inherent performance deficit that no amount of airmanship or tactical cleverness could fully negate. The origin of this edge traces back to peacetime chemical research rather than wartime engineering. Petroleum scientists understood that an octane rating reflects how much an air-fuel mixture can be compressed before it detonates prematurely. Higher allowable compression yields more power per cycle, producing faster airplanes and greater operational ceilings. The science was conceptually simple, but scaling production of truly high-octane aviation gasoline required difficult engineering. In 1940, U.S. aviation fuel production still centered on 87-octane gasoline, fine for civil aircraft and basic trainers but hopeless for high-performance combat engines. The British, urgently seeking any edge against the numerically stronger Luftwaffe, partnered with American oil firms to produce 100-octane fuel in time to influence the Battle of Britain. The effect was immediate. Spitfires and Hurricanes running 100-octane gained 30-40 mph at altitude and climbed 500-1,000 feet per minute faster, erasing the Germans' earlier performance advantage. The move to 130-grade fuel represented another significant jump. With a performance number of 130 on rich mixture settings, this blend became the workhorse of Allied air power through 1943. Powering Merlin engines in Spitfires and early Mustangs, Allison engines in P-38 Lightnings, and the massive Pratt & Whitney R2800 radials in P-47 Thunderbolts. Production expanded quickly thanks in part to aviation fuel advocates like General James Doolittle, who had spent the 1930s persuading military and industry leaders to invest in high-octane fuel research. By 1943, some 17 Allied refineries were producing high-octane aviation gasoline using catalytic cracking techniques refined by émigré engineer Eugène Houdry. American refineries alone were turning out millions of gallons per month, enough to sustain the strategic bombing campaign and the expanding fighter forces that escorted it. German fuel output, by contrast, remained constrained by its coal-to-liquids approach. The Burgess process and related synthetic routes were technically sound but slow and resource-intensive. Even at peak capacity, Germany produced only a fraction of the high-performance aviation gasoline the Allies could supply. Most German fighters therefore burned B-4 fuel rated around 91 octane on the lean scale. Their superior C3 blend, used in certain BMW 801-powered FW190s and some Messerschmitt variants, was roughly comparable to Allied fuels in the low 130s, but was available only in limited quantities. By 1944, perhaps two-thirds of German aviation fuel output was C3 grade, but that still amounted to only a small portion of Allied production. To understand why this mattered, it helps to grasp how internal combustion engines respond to compression. Octane numbers indicate resistance to detonation. When a piston compresses the air-fuel charge, pressure and temperature rise. If the mixture auto-ignites before the spark, detonation occurs, an uncontrolled explosion that sends shock waves through the engine and can cause catastrophic damage. Higher octane fuels tolerate greater compression without detonating. The traditional octane scale uses iso-octane as the 100 reference. By definition, a fuel cannot have an octane rating above 100 on that scale. So engineers instead used performance numbers to express how much better a blend behaved under rich, war settings. A performance number of 150 signified that the fuel could endure significantly more compression than pure iso-octane before detonating. Producing such fuel demanded anti-knock additives, chiefly tetraethyl-lead, and carefully chosen aromatic components like toluene and xylene blended into the base gasoline. British chemists at the Royal Aircraft Establishment ran extensive trials through 1942-43 to find an optimal mix of anti-knock properties, energy density, and manufacturability. American researchers at Wright Field conducted parallel work and exchanged results with their British counterparts. By early 1943, both nations had produced test batches labeled 150 grade. The label was somewhat misleading. It suggested an octane figure of 150, which the scale didn't really allow, but it denoted a fuel that combined 100 octane behavior on the lean scale with a performance number of 150 on the rich scale. Dyed purple for quick identification, the fuel underwent rigorous testing during 1943 and performed even better than hoped. Merlins using 150 grade fuel could sustain manifold pressures around 75 inches of mercury, compared with roughly 67 inches on 130 grade fuel, directly translating into greater horsepower. A Packard-built Merlin V1657, the engine that would power later P-51 variants, produced about 1,490 HP at standard military power on 130 grade gasoline. Running 150 grade at war emergency settings pushed output well above that. Figures in various tests approached 1,220 HP for certain Merlin variants, and the V1653 and early P-51B tests saw outputs near 1,600 HP under those conditions. Flight trials at Wright Field confirmed sizable gains across speeds and climb regimes. Top speed at altitude rose roughly 25-30 mph. Climb improved by several hundred feet per minute. And crucially, none of this required altering the airframe. The same Mustang that flew on 130 grade one day and 150 grade the next became noticeably faster and more capable simply because of what was burned. The decision to introduce 150 grade fuel into frontline fighter units was taken in early 1944. The timing was deliberate. The 8th Air Force, flying daylight strategic bombing missions from England deep into Germany, was suffering losses it could not sustain. Although the first P-51 Mustangs had arrived in December 1943, German fighters continued to inflict heavy casualties on American bomber streams. Planners needed more than a long-range escort. They needed an escort so quick that German interceptors could not easily disengage or choose the terms of battle. In May 1944, the first operational shipments of 150 grade fuel reached England. Its distribution was tightly managed. Not every squadron received it at once. The 8th Air Force prioritized selected units both to handle supply constraints and to assess combat effects. The Royal Air Force, which had driven much of the early testing, also began issuing the fuel to its squadrons. Priority went to units assigned high-speed interception duties, especially those tasked with hunting V-1 flying bombs that began terrorizing London in June 1944. The V-1 cruised around 400 mph near the ground. Intercepting it demanded fighters that could match or exceed that velocity at low altitude, where denser air sapped performance. Hawker Tempests and late-model Spitfires struggled to catch many V-1s. Mustangs on standard fuel were marginal. Mustangs on 150-grade fuel, however, had the surplus speed needed to intercept reliably. On June 18, 1944, Major R.E. Turner of the 356th Fighter Squadron destroyed a V-1 by using his P-51's wingtip to tip the bomb's wing, a tactic later used at least 16 times during the campaign. The move required exceptional speed and precise control to place the fighter's wing within roughly 6 inches of the V-1, then use the disturbed airflow to roll the bomb off course. Widespread frontline use of 150-grade fuel by American P-51 units began in June 1944, coinciding with the Normandy invasion. 8th Air Force fighter groups, charged with securing air superiority over the landing zones, flew patrols and escorted bombers while using the new fuel. German pilots started filing reports of Mustangs performing beyond prior expectations. Luftwaffe intelligence collected pilot accounts describing American fighters that seemed uncapturable across flight regimes, able to accelerate away from interceptors, and showing inexplicable power reserves. Initially, these reports were shrugged off as pilot exaggeration or the effects of fatigue and stress among beleaguered German airmen. That judgment was mistaken. The full truth only emerged after the war. Ace pilots like Gerhard Barkhorn, who scored most of his 275 victories on the Eastern Front, later recalled in post-war interviews being astonished by late-war Mustang performance when flying against Americans over Germany in 1944. Test flights of captured P-51s, P-47s, and P-38s reinforced those impressions. The Mustang's speed, climb, and high-altitude capability stood out. What German pilots had not realized in combat was that they were facing aircraft whose capabilities had been boosted chemically well beyond original design limits, engines running at power settings the designers had not planned for. The Rolls-Royce Merlin, built in the U.S. under license by Packard, had been engineered with careful thermal and mechanical margins. Pushing boost pressure moved those margins nearer danger. The revolutionary aspect of 150-grade fuel was that it let engines run at extreme boost without suffering the destructive detonation that would have destroyed engines, fueled with lower-grade blends. The chemistry behind this involved how fuel molecules interacted with air, heat, and pressure in the combustion chamber. Tetraethyl-lead, the main anti-knock additive, interfered with the chain reactions that caused spontaneous ignition. There were costs. Tetraethyl-lead was toxic and required careful handling, and it deposited residues on spark plugs, valves, and cylinder walls, increasing maintenance needs. The heavy lead content of 150-grade accelerated fouling and cylinder wear. Ground crews adapted rapidly. Spark plug change intervals were shortened, cylinder inspections grew more frequent, and overhaul timetables were revised. The operational staff judged the extra maintenance acceptable for the performance gain. Pilots also adjusted procedures. Manifold pressure limits were raised, and crews had to avoid overboosting, especially at low altitudes where air density was greatest. Managing fuel consumption became critical. 150 grade provided far more power, but full war emergency settings burned fuel quickly. Long-range escort sorties, such as missions to Berlin, already stretched the Mustang's endurance. Using the new fuel to its fullest required disciplined throttle management and knowing when to conserve for the return leg. Combat reports through the summer and autumn of 1944 document the effect. 8th Air Force fighter groups using 150-grade fuel logged improved kill-to-loss ratios and greater success intercepting German attackers aiming at bomber formations. Fighters that once could dash in, strike, and escape now found themselves unable to outrun pursuing Mustangs. On August 6, 1944, Lieutenant Hollis Bud Nally of the 357th Fighter Group flying as part of Operation Frantic missions to Soviet airfields, encountered German fighters over Eastern Europe. Flying his P-51D called Hell's Bells and fueled with 150-grade gasoline, Nalin engaged a Messerschmitt Bf 109 piloted by Gottschalk. During the dogfight, Nalin's speed advantage proved decisive. He closed rapidly, fired a short burst that crippled the Germans' cooling system, then, low on both fuel and ammunition, broke off and saluted the enemy before returning to escort duties. Schack managed to belly-land his damaged fighter near German lines. For 4 decades, Schack wondered why the American hadn't finished him off, unaware that Nalin believed he had only inflicted damage rather than destroyed the aircraft. When historians later brought the two men together for a meeting in Germany, Schack admitted the Mustang had shown capabilities he'd never seen before. The rapidity of Nalin's closure and the visible power reserves were unlike prior encounters with U.S. fighters. The psychological impact on Luftwaffe airmen was profound. Already outnumbered and increasingly pressed by Allied strengths, they now faced American fighters that seemed to possess near-limitless performance. Their tactical choices narrowed. Massed attacks might still overwhelm escorts, but at ever greater cost. Remaining on the ground preserved scarce pilots and planes, or engaging risked being outpaced and shot down by Mustangs that enjoyed both superior speed and growing confidence among their pilots. Reichsmarschall Hermann Göring, observing P-51s over Berlin, is said to have commented that the war was lost, a reflection of the Luftwaffe's strategic predicament. The Mustang's long reach meant no part of Germany was safe from daylight raids, and the mid-1944 rollout of superior fuel only worsened that crisis. Luftwaffe technical intelligence eventually recovered samples of Allied 150-grade fuel from captured drop tanks and wreckage. German chemists analyzed the samples and confirmed what pilots had reported. The Allies were using aviation gasoline with performance traits beyond the output of Germany's coal-to-liquid plants. Some post-war German accounts claimed late-war C3 blends neared 150 in performance, but production was too limited and quality too inconsistent to matter strategically. Allied air attacks on synthetic fuel facilities, notably raids in May and June 1944, further crippled German production. By late 1944, fuel rationing had become routine. Fighters received priority allocations but still faced severe restrictions. Training hours for new pilots were slashed. So many arrived at combat units with far less flying experience than their American counterparts, who typically logged several hundred hours before frontline service. Loss statistics illustrate the change. From January to May 1944, before 150-grade fuel was widely used, bomber loss rates averaged roughly 3 to 6% per mission. Painful, but sustainable. From June to December 1944, after the new fuel's introduction and as air superiority was established, loss rates fell to below 2% per mission. Fighter claims surged. P-51 groups across the 8th, 9th, and 15th Air Forces reported about 4,950 German aircraft destroyed in aerial combat from late 1943 through May 1945, with a large share occurring after June 1944. The once experienced German pilot cadre, already weakened by Eastern Front attrition, was being depleted systematically. By D-Day on June 6, 1944, only 2 Luftwaffe aircraft were seen over the invasion beaches. Germany still possessed thousands of fighters on paper, but lacked the fuel, trained crews, and tactical flexibility to employ them effectively. The technical details of 150-grade fuel are worth noting. Its lean mixture octane rating of 100 resisted detonation at cruising settings as well as pure iso-octane, while its rich mixture performance number of 150 meant it tolerated roughly 50% more compression than iso-octane under maximum power. That dual behavior allowed pilots to cruise efficiently for range and then switch to rich mixtures for combat without fearing detonation. Handling the fuel demanded extra safety measures because of its high tetraethyl-lead content. Ground crews wore protective gear, spills were cleaned quickly to avoid lead exposure, and storage and transport were clearly labeled to prevent cross-contamination. Despite the toxicity concerns, serious industrial accidents were uncommon. Introducing 150 grade into operational units required updated pilot instruction and engine procedures. Manifold pressure limits were revised and clear rules set for when to use war emergency power. Aircraft required no hardware changes. Engines and fuel systems tolerated both grades, which simplified logistics. The production figures underscore the industrial gap between Allies and Axis. From May 1944 to April 1945, the 8th Air Force alone burned more than 53 million gallons of 150 grade fuel. Allied refineries collectively likely produced over 200 million gallons for operational use. Each gallon demanded refining capacity, additive supplies, notably tetraethyl-lead, quality control, transatlantic shipping, secure storage, and distribution to dozens of airfields. American wartime industrial output. Factories churning out bombers by the thousands, fighters in the tens of thousands, shipyards launching Liberty ships faster than losses, and refineries generating aviation gasoline in volumes Germany could not match, underpinned the strategic advantage. Decades of industrial buildup, abundant natural resources, a homeland shielded from enemy bombing, and a wartime workforce that mobilized millions of women into factory jobs produced an economic output the Axis could not match. The Royal Air Force made widespread use of 150 grade gasoline in European fighter operations. British squadrons flying late-model Spitfires, Tempests, and Mustangs received priority allocations and reported the same kinds of performance gains American pilots had described. The Tempest, already one of the fastest piston fighters, became even more lethal. Tempest units scored huge successes against V-1 flying bombs. Between June and September 1944, RAF Tempest wings using 150 grade fuel accounted for hundreds of V-1 kills, with No. 3 Squadron alone claiming over 300. Individual scores included Squadron Leader Joseph Bry's 59 V-1s, Belgian ace Remy van Laerde's 44, and Wing Commander Roland Beaumont's 31. Mosquitoes shot down 623 V-1s, Spitfire Fahrtrittaders 303, and Mustangs 232. The advantages of the fuel showed up in every mission type. Through late 1944 and early 1945, units equipped with 150 grade reported higher victory tallies and fewer losses. By March 1945, nearly all P-51 units were using the fuel, and combat records from that time show overwhelmingly one-sided encounters. German fighters seldom mounted effective opposition, and when they did, they usually paid a heavy price. In April 1945, many missions over Germany met no aerial resistance at all. The Luftwaffe had been broken by sustained attrition, crippling fuel shortages, and the steady depletion of veteran aircrew. On May 8, 1945, Germany surrendered, ending the air war in Europe with unchallenged Allied air supremacy. That supremacy sprang from many causes. The Mustang's long range, superior American pilot training, massive Allied numerical superiority, and an industrial base that outproduced Axis rivals. The petroleum engineering edge provided by 150 grade fuel, however, was a crucial factor. The purple-dyed gasoline turned already capable fighters into markedly superior machines, bolstered pilot confidence, and represented the concentrated technical and manufacturing power of nations able to outproduce and out-innovate their foes. Speed in aerial combat confers choice, when to attack and when to withdraw, and the combination of a well-designed airframe and higher performance fuel gave Allied pilots tactical options the Luftwaffe could no longer match. By late 1944 and early 1945, the operational contrast was stark. Allied fighters could fly multiple combat sorties each day, limited mainly by crews and upkeep. German fighters frequently remained grounded because of fuel shortages. When Luftwaffe units did fly, they were constrained by rigid fuel conservation rules that reduced their combat effectiveness. A German pilot who expended too much fuel in battle risked being unable to return to base. Allied pilots, on the other hand, could employ war emergency power when necessary and still rely on sufficient reserves for the trip home. That operational leeway had strategic consequences. Allied units maintained patrols, reacted aggressively to threats, and sustained operations continuously, while German units had to pick fights carefully or simply sit out missions. The story of 150-grade fuel is fundamentally an industrial one. Winning required not just more aircraft but better performing aircraft, not just fuel but superior fuel, and not just trained pilots but a surplus of well-trained personnel backed by an industrial system that could replace losses faster than the enemy could inflict them. British and American fuel chemists and refinery engineers never flew the combat missions their work enabled, yet their lab and factory achievements, measured in performance numbers and allowable manifold pressures, helped determine control of Europe's skies in 1944-45. Each time a P-51 pilot shoved the throttle forward and felt his Mustang surge beyond what German fighters could match, that advantage traced back to chemical engineering that converted crude oil into a fuel that made exceptional performance routine. German planners had expected American fighters to behave within predictable parameters based on airframe design and standard fuel. Instead, they confronted aircraft whose real-world performance exceeded those assumptions, sustained by a fuel production apparatus so large and sophisticated Germany could not counter. By spring 1945, Allied armies pressed into Germany from both east and west, while the Luftwaffe had effectively ceased to operate as a coordinated air arm. A handful of units still flew, often with barely enough fuel for a single sortie. Advanced German jets like the Me-262 represented technological progress, but arrived too late, in too few numbers, and were hamstrung by fuel scarcities and the loss of experienced pilots. The aggregate numbers make the point. American P-51 groups flew hundreds of thousands of sorties, claimed roughly 4,150 enemy aircraft destroyed in air combat, and another 4,131 destroyed on the ground. Those figures represent more than hardware lost. They reflect pilots killed, expertise erased, and German industry expending resources to build replacements that were destroyed before they could change the strategic balance. 150-grade fuel was not the sole cause of Allied victory, but it was a significant contributor, an industrially produced edge that turned close fights into decisive wins. The roughly 448 MPH a properly boosted Mustang could reach signified not merely speed but technological superiority and production capacity the Germans could not match, that American fuel chemists and refinery engineers working far from the front line could create an advantage as potent as any weapon system was a striking irony. Purple-stained gasoline, pumped into tanks and burned in powerful engines, helped determine aerial dominance mission by mission. The P-51s that crossed Berlin in early 1944 were remarkable. The same airframes in early 1945 running on superior fuel were faster, stronger, and more lethal. Measured in octane and performance numbers, manifold pressures and airspeed readings, that chemical edge was one of many decisive differences